So, welcome back. Happy last 2 weeks of the semester. And as I was mentioning before we got started here, you are really almost done. Certainly, in terms of this class, we do have this project part C, but it is scaled back significantly. And our exam is really an end term versus a final exam. And so, in terms of where we are in our schedule, uh, you know, we're really close to done. So here we are in what should be the second week topic of cache memory. We'll be fine. We'll cover enough of the big picture topics here. So there's a comment about you can't see it. Can you not see me, or can you everyone see what they need to see right now, or is there some other issue I have to correct before we get going here? The poll. Oh, maybe I didn't click share the results. So now you don't know. It was roughly in the medium. So okay, fine. Thank you. Everyone's feeling okay, but not great, which I think is fair and correct. Thanks for letting me know. I might have clicked the wrong button there. Just looking at where we were, we didn't do a quiz last week, and I didn't update this schedule. Don't sweat it. So what we're going to have is a quiz this week, and I'll just move quiz 10 up, move quiz 11 up to quiz 12, and then not do a quiz 12, and that's fine. We don't need to have 12 quizzes. There's nothing magical about that. I also would love for everyone to do the course evaluation survey for this class. Your feedback is very valuable to us. And so I'll provide you a quiz score, basically a participation credit for filling that out as well. I don't get to see how you filled it out. I just get to see whether you filled it out or not. You should get an email about that. And it's also just available in Canvas under the surveys tab in Canvas. So don't have to do that right now during class, but at some point before the expiration date for that, please do fill out that survey. Those things are kind of important. I mean, I've gotten a lot of feedback as we've gone. A lot of you have not been afraid to share your feelings about how things are going this semester. So I'm not expecting anything shocking. But the university cares about these things. My boss cares about these things, and so it's like when when you order McDonald's and they ask you to fill out the survey online. It's kind of the same thing. So you've had your happy meal this semester. So now please fill out the survey after the fact, and you may in fact win a prize. There's no prize. Okay. So we were talking about cache memory on Friday, and we were kind of crossing over topics. And I think we got lost a little bit in the weeds in terms of like the underlying SRAM and DRAM. And I could tell it's a topic that you already have as a class some fluency in terms of knowing what memory is about and why it's important. Maybe just from previous classes, maybe just from configuring and building your own PCs or purchasing laptops in the past. I think from the computer architect's viewpoint, where we're not necessarily getting the weeds of VLSI, although we could, this view of the system is probably sufficient for our purposes, which is, we've been spending a lot of time focusing on the main data path. But in order for this whole system to really work in practice, we need a much more efficient way of accessing our memory, our main memory, our data that's stored presumably here, but potentially even further away, and even in a slower resource than in our main memory. And that's the role that the caches play in our system. It is a relatively small amount of relatively fast memory storage that ideally, every time we're requesting an instruction fetch to be fetched, or we're reading or writing a load word or store word into our memory, it's actually going to be happening here, and we don't have to get over here, or very infrequently do we have to actually do requests that are over here, and that allows us to keep our pipeline full, and that's why we want to be able to do that in our system. um, Little confusing what it means to be a CPU anymore, or even what the term processor really even means anymore. Where one actually draws these dashed lines um, changes on an annual basis. That's not a fixed thing in terms of what is all on a chip. And if it's on a single chip, is it in the same package, or is it multiple dies inside the same package, or is this other component further physically away from the CPU? Um, we don't really get to any of those true sort of system fabrication and integration results. The trend is to condense as much as possible into a single package, if not a single die, so that you will see in more modern designs, 2020 architectures, what the term processor is versus memory isn't really that clear, because the goal is to put as much of this, even as much of the main memory as you can, inside a single package there, for the same reason that closer is faster, right? The further my signals have to travel, just like in our critical path analysis, the further they have to travel, the slower it's going to wind up ultimately being. So to meet goals of timing and performance and resource usage, trying to smush as much as possible into the single chip view is the trend we've seen here. From our perspective, in terms of understanding how caches work, it doesn't really matter if it's an on chip cache, which they almost all certainly are today, or if it's something that's physically further away. We care more about the logical relationship between the instructions and the data that we're fetching and how they're actually being stored in this hardware managed cache memory here. But otherwise, I do think this is I'm not going to say a straightforward topic. It's a topic I think that based on what we've already learned, I think your intuition will prove to be correct the majority of the time. There's no tricks here, I think, with this concept. So actually, I'll go back one slide here. So that's the concept. This is where we left off on Friday. That the idea being that you have your large storage, your main memory, your DRAM storage here, and wouldn't it be nice if there was a balance between fast and extremely small, and large and relatively slow. And that's the role that our cache is playing. That ideally, the vast majority of our accesses are going to be satisfied via this module that we have here for both instructions and data. And consequently, we have this large backing store, but we don't need to access it very often because that'll be very slow if we have to do so. And the main big picture concept that allows our caches to work, not just in theory, but also in practice, is this principle of locality. So it's usually quite difficult to know exactly which data your program is going to access. There's ways you can do that analysis, but there's limits to the type of static analysis, offline analysis you can do regarding whether this branch is going to get taken and consequently whether this data access is going to be needed or not. So knowing it in advance is actually kind of hard to do. So you can't necessarily preload values necessarily into this cache memory. But what happens in practice is that most programs exhibit this concept referred to as locality. And we separate those into two different types. And that's temporal locality or just locality in time. And the principle temporal locality, and this is our big picture concept here, is that if you're accessing a memory address, if your program needs to read or write either an instruction or a data value at a particular address, it's very likely to want to do it again in the future. Again, it's a principle, it's an empirical observation of how programs tend to operate. It's not some immutable law. You could very easily write a piece of code that exhibits zero temporal locality. You could randomize your memory accesses and just randomly spray things around in memory, and you'd have very bad temporal locality. The likelihood of repeating an access would be quite low. Again, the idea is that this is in practice, this is what programs tend to show. If I accessed a value in memory, I'm likely to want it again. That is somewhat compared or contrasted to this concept of spatial locality or locality in space. And space referring to just contiguous locations in my memory. So that principle indicates that if I'm accessing a location, an address in memory, again, either an instruction or a data value, I'm likely to also want to, in the future, access nearby things. So locality in time means I'm likely to repeat my requests. Again, just in practice, that tends to be the case, that our programs do exhibit these types of locality. And then spatial locality is that if I'm accessing A of I, I'm very likely to want to access A of I plus 1 soon. Again, neither of these are guarantees that's guaranteed to be the case, that if you do one of those, you're likely to either do it again or do something nearby. Just in practice, programs we tend to write, the resulting assembly code that gets generated tend to exhibit, by and large, locality of those two types. And here's just an example of what temporal locality means in programs, or in instruction memory would be a better way to phrase what that's referring to here as opposed to in programs. Again, temporal locality says that if we access one memory address, we're likely to do it again. So I think a better way to word this would be temporal locality in instruction memory versus in programs. But our best example of where we find temporal locality in our instruction memory accesses would just be due to loops. So we have this loop, and the idea is that if you have a loop, you're likely to iterate a number of times. Again, we can't say anything more precise than that, right? Just like our rule of thumb regarding how frequently branches are showing up in our code, other basic rule of thumbs that we tend to learn through decades of empirical observation, this is another example of those. Our code tends to have loops. It's a very powerful thing to have in our code that we write. And because it tends to have loops, the code that we write tends to have locality of temporal locality in our instruction memory. Again, the idea being that once we've fetched this instruction, this load word instruction, because it's in a loop, there's a pretty high likelihood that we're going to want to access it again. And not just a second time, right? We're going to want to access it many times. Depending on how much that loop iterates, we may have to access it 100 times or a billion times. That's temporal locality. Again, locality just in time. Temporal locality in data is also something we've seen to some extent so far, right? Where if you're accessing the same variable over and over again, this is the same use case for why we have registers in the first place. This is also our use case for why we have to worry about dependencies in our code. But right, we have a register value, or we have a variable value, and we have it for a reason. We want to write to that value because we want to read it again. Or conversely, if we read from a value, we're also likely to need to read from it again in the future. Those data dependencies exist throughout all of the programs that we write, either at the source code analysis we could do here, or we've done it at the assembly level now. And so that's temporal locality in terms of our data memory. And again, you may say, well, we don't have to worry about caches for temporal locality in data because that's what our register file is. And we got to a little bit of a semantic sidetrack on Friday where I talked about how the term cache is kind of a relative term, right? Our register file can absolutely be thought of as a type of cache for our cache, right? And then our cache is our cache for our main memory, and our main memory is a cache for our disk, and our disk is our cache for cloud storage or internet access or things like that. So yes, absolutely, because we're going to access these variables many times in the future, because it's going to exhibit a high amount of temporal locality, putting them in the register file is a good idea. The downside of that, or the limitation of that, is our register file tends to be limited. It's a matter of degree. It's that much even smaller than what our SRAM caches would be, so we can store less data, but it's going to be faster. So it's the concept still applies to our register file, but it also applies to things that don't necessarily fit into our register file. And then there's just coding patterns that limit the use of registers directly. If we need to do operations on pointers, those pointers themselves could potentially be stored in the register file, but we can't then take the address of a register. We can only take addresses and have pointers to things that have a main memory location. So we have to have some other place to store those potentially efficiently using a cache structure. So again, spatial locality, so temporal locality, time. That's all you need to think about. Temporal, just fancy way of saying locality in time. Stuff repeats. Spatial locality, think space, but don't think like outer space. I mean, you can think outer space if you want, but think nearby locations. Neighborhood locality is our spatial locality. Again, if we access one memory address, there's a good chance or a high likelihood we're going to want to access other nearby addresses. Spatial locality we see all the time for somewhat obvious reasons, but if we think about instruction memory spatial locality, it's a byproduct of our PC equals PC plus 4, right? We fetch a value at PC. There's a very high likelihood, unless it's a branch, right? So for the vast majority of our instructions, if we've accessed an instruction at PC value, whatever, there's a very high likelihood we're going to want to access the next one, and then the one after that, and then the one after that. So this code isn't necessarily doing anything all that interesting from an instruction perspective, but it has a very high amount of spatial locality in instruction memory. As soon as we fetch this, there's a high likelihood we're going to want to fetch the nearby ones. So that's kind of a gimme, right? It's always going to be there in our programs. We would have to work pretty hard to write a program that did not exhibit temporal locality in our instruction memory. You could, right? You could write a program that's continually jumping all over the place and never doing PC plus 4 ever and still trying to get work done. You'd have to try pretty hard to do that. Naturally, programs exhibit a large amount of spatial locality. And then spatial locality in data, first off, that previous example also was showing spatial locality in data, right? Because we were doing stack pointer, offset 0, 4, 8, 12. So just our stack bookkeeping code, which I think we flushed from our memory because we haven't had to do that much of it this semester. Depending on if you implemented merge sort, you'd have to worry a little bit about a stack. That's also spatial locality in data, because we've accessed data memory at stack pointer. For this particular code, we're also accessing stack pointer plus 4 and plus 8 and plus 12. That's spatial locality in data memory from the MIPS assembly perspective. But we also could think of it from our C coding perspective as well, right? when we have arrays in our code, and I already mentioned this briefly, we have a of I, we're likely to want to access a of I plus plus at some point in the near future. Also, structures also involve spatial access to memory, right? To data memory. If we have structures, if we're going to access one field in a structure, we're very likely going to want to access nearby fields in that same structure that are going to correspond to spatially local data memory addresses. So, a very brief rhetorical question. Show me a thumbs up or a thumbs down using your Zoom interface here. Can data have both spatial and temporal locality? I guess yes, and well, I said thumbs up, but now I'm seeing some yeses. So, well, okay, I'll count yeses as thumbs up. That's fine. I got you. No, then the Zoom window. I don't need to see your physical thumb. That's fine too. Nobody's arguing for no, so I think we got it. The answer is yes, I guess, right? Um, this example up here is showing that spatial locality of a of I. But if that loop was an inner loop where for which there was an outer loop, j loop, then not only will we access a of I and then subsequently a of I plus 1, we'll also access a of I followed by a of I at some point in the future. Just like our data dependencies, where we don't really quantify the amount of data dependencies, and we also don't necessarily quantify when we're doing our high level analysis here, how far away does that data dependency need to be for us to no longer care about it? The same could be said for locality as well. If I access a of I today and then I access a of I next month, program could do that absolutely, right? Is that temporal locality or not? Um, Technically, I think it is. It's a slippery kind of slope as to what extent we care about it if it's that far away in the future. But conceptually, though, the principle still applies that we access something, we potentially want to access nearby locations, and we also potentially want to repeat those accesses. You'll see in diagrams cache being indicated by the dollar symbol in an architectural diagram. You may have already seen that in the textbook or in other things you've seen online. For instruction cache is sometimes labeled as I dollar sign. I just drew it as cache here, but you'd separately see it as I dollar sign and D dollar sign. That's just a really awful play on words, basically. So cache. That's why you'll see that time and time again. It's just one way of doing a shortcut for referring to cache. I don't know how well that translates, but that's why you'll see I dollar sign and D dollar sign for instruction cache and data cache there. So taking advantage of temporal locality to begin with, uh, kind of automatic, or it's kind of the fundamental principles of how any sort of cache works. Well, we will talk about spatial locality as well. It's equally important. But taking advantage of temporal locality just kind of works based on having this structure in the first place, right? The idea being the first time you have that load word, or the first time you fetched that instruction, it's presumably not going to be here to begin with. That's the assumption. So it's going to be, and we'll use the right terminology eventually, it's going to be a miss in our cache. We've requested something and that is a miss in our cache because it wasn't there. And we don't know it's there or not until we check. So we attempt to check, we discover that it's not in the cache, we've missed. We eventually have to then go through the rest of our memory controller and find it eventually. We can take advantage of that though. So on our first miss, on our first request to either a program counter or to a data address that we've calculated, if it's not in the cache, as we're grabbing it from our main memory, we also then put a copy of it in the cache, right? If you think of a load word instruction, load word puts a value in our register file. And it still does that in this case. If we have a cache in our system, sort of transparent to our software's perspective, we're not just taking the value that we're loading word and putting it in our register file, which would be located here conceptually. We're also taking a copy of that value and putting it in our cache. So that first read, that first request to an instruction address or to a load word address that we haven't done before with regard to our temporal locality is going to be a miss. So it's going to be slow. Even slower than if we didn't have a cache, right? Because there's two sequential things that are happening. First, we check the cache, and then we go and check main memory. So it's going to be a little bit slower than if we didn't have a cache at all. But then ideally, after that first miss, our subsequent request to that same address, which again, as we see, will happen in our programs. We'll be fetching the same instructions multiple times. We'll be loading and storing words to the same value multiple times. Our subsequent accesses are going to be accessed through the cache. We haven't talked about how we do that. That's conceptually what it means to have a cache, to store that most recently used copy. And so for temporal locality, I wouldn't say that's automatic, but that's the whole principle. We have a cache so we can take advantage of temporal locality. To take advantage of spatial locality, we have to be a little bit more careful, I guess I would argue, right? We have to make sure we not only just grab the value that we wanted, we did a load word or we did a program counter corresponding to an instruction fetch. We have to not only grab that value, because we want to potentially take advantage of spatial locality, we also are then at that point going to want to grab nearby values. So arguably our initial misses are going to be even worse in this case than in the previous case where we weren't potentially doing that. I have a program counter value, right? That 40 million hex that you start your program counter at for your Mars code. It's going to be a miss in our cache. We would then have hardware, our logic. This wouldn't be software managed. This would be a piece of memory management piece of hardware here, a memory controller here that would then say, give me instruction or the value at that 40 million hex. And while you're there, give me 40 million in 4, give me 40 million in 8, give me 40 million in 12. To some extent, we have to design that parameter. How much do you give me when I'm actually really only needing a particular address at any given time? And we put all of those values in the cache, right? The load word only actually returns the value that we need for that particular instruction. So that's the only value that goes in the register file, but all that neighborhood goes in the cache. And that's how we would potentially take advantage of spatial locality. The term gamble is being used here. It's a type of prediction, kind of like our branch prediction, but also it's a more obvious prediction to make because programs tend to exhibit that spatial locality. If we're already going to have to go off to main memory and pay that penalty, let's pay a little bit more penalty. It's not 4x the penalty to access 4 things. Usually there's an initial sequential access time. Excuse me. There's an initial non-sequential access time to get started, which is quite high. And then sequential accesses after that initial non-sequential access is relatively modest. It's pipelined as well in the memory controller for your main memory. So we're already paying a pretty hefty penalty because our data wasn't in the cache. Let's pay a little bit more penalty, and the hope is that for those next few accesses, they're going to be in the cache for us. So there's this concept of that's a valid question. So if you start moving up the memory, does it load values in front of you? Well, in this instance, that's exactly what it did, right? For access I, it did load the value in front of me. Well, in front, sequential and location, right? I requested only I. In the process, it's loaded I plus 1, I plus 2, I plus 3. How many it loads is a parameter of our cache, referred to as the block size, and we will get a chance to talk about that. There's also a separate unit that many architectures use referred to as a prefetcher. And that one is even trying to be more speculative. It can analyze your program and determine, and you can sometimes kick it off in software as well and say, hey, I don't actually need anything near here right now, but I have a feeling I'm going to need it in the future. Go put that in the cache for me so that when the time comes, I don't even pay that initial penalty of my value. Yeah, so whether it does that or not really would depend on if there's a prefetcher. There's going to be a parameter of our cache that tells us how far sequentially from our current address do we load. That's kind of prefetching in a sense, but then there is a separate hardware mechanism referred to as a prefetcher that tries to even speculate even more than that. Go even further and load a few other blocks into our cache just in case. If you didn't need them, no harm, no foul. Technical term. And okay, we talked about this concept already, right? The term cache is kind of overloaded. It's even overloaded in the context of computer architecture, but just overloaded in terms of computing. Networks are probably the best example. We talked about your internet cache, right? It's a cache where the data is actually on your hard drive, and that itself is a cache for going to the network itself. We have to be careful about that, right? Sometimes you want the value that's stored in the cache. Other times, you actually want to pay the penalty and go grab the newer, more fresh data here. We won't really get to talk about TLBs or virtual memory this semester. We're supposed to. It's in the syllabus, but we're not getting to it. But in 308, you'll get to that. So, or in 352. When you talk about operating systems, there's a separate custom cache specifically to support virtual memory. and it's a way of keeping track of the most recently translated virtual to physical addresses. So that's something we'll not talk about. I won't even mention TLBs again. That's something that should be covered in a computer architecture course. Fortunately, if you're a computer engineer or a software engineer, you have to take an operating systems class, and you will learn that. If you're a double E, well, it's been a tough semester. Some of the terms we've already started to define, but we do need to be pretty precise when we refer to analyzing caches. So a cache hit. Um, I don't know why is it called a hit versus a success or something like that, but that's just the term that was invented that has been used and is an official term or a very commonly used term. A cache hit is when we request data and it's in the cache that we're looking for. That's it. That is a cache hit because it's got the data. That's a good thing. We want that to happen. The converse of that is a cache miss. We requested something in the cache and it doesn't have it. This is bad. We now have to go to main memory and access the values from there. And so we can take that information, whether there was a hit or a miss for a particular access, and calculate what's referred to as the hit rate and or the miss rate. They're complementary terms here, right? The hit rate is just the percentage of the time that that we in practice have a value that we're requesting in the cache. And the miss rate is just the complement of that, right? So if I have 100 accesses to my main memory, um, and 95 of them were found in the cache first, that's a hit rate of 95% and a miss rate of 5%. And it turns out, even though these caches are significantly smaller than our main memory, right? We didn't go into real detail of the actual values, but your caches will have values of like 16 kilobytes of storage or 32 kilobytes of storage. They do get larger than that, but you'll certainly see caches of that size versus a main memory that's gigabytes of storage, right? 8 gigs, 16 gigs, 32 gigs, and so on, right? Even with that, you wind up seeing that these caches, if they're designed carefully, and if you have a program that behaves as a typical program does, you will see these caches that have very high hit rates 95, 97, 99% hit rate for these caches. And that's a necessary thing for our pipeline to have any purpose for us. We keep our pipeline happy and full because even though the cache is really small, and even though it's not guaranteed to have anything that we want, it just in practice happens to have the stuff that we want a good percentage of the time. And that 90 some percentage of the time is a very typical cache hit rate for our cache, even for a small cache. So let's start with a very basic cache design. Then the principle still applies to a cache of any size. So I think this is personally a nice thing. Unlike our pipelines where we covered our 300 level textbook pipeline, and then as we showed some pictures and some diagrams, the real pipelines they look kind of similar. You can kind of squint your eyes and see your pipeline, your 5 stage out of these much more complex pipelines. For caches, there really hasn't been much fundamental change in the last 20 years or so. So we will start with a very basic cache, and the cache in the processor that you're using right now to connect to the Zoom looks extremely similar. Different parameters, but is doing the same exact thing by and large. So we talk about caches being divided into blocks, which are various sizes, but it's almost always going to be a power of 2. And that's a common thing for memory sizing and memory storage to have things be a power of 2. It makes our address calculation math usually pretty simple. It allows us to just grab the right bits of our address as opposed to doing divisions and remainders and things of that nature. So it's very common when you want to pick a memory size, and cache is no different to have it be a power of 2. For now, just to keep this design something that we can just do on a PowerPoint slide, we're starting with a cache for which each block is 1 byte. That's not something you'd want to use for a MIPS processor. You'd at least want it to be 4 bytes for load word and store word. And then similarly, having a 1 byte block means there's no spatial locality going on here at all. But that's okay. We'll start with that, and then we'll add some more details here. So here's our 8-block cache. You could also refer to it as an 8-byte cache. It's the same concept. There's a block size of 1 byte, and there's 8 of these blocks, and each of them are just storing 1 byte. So the 4 important questions as we design a cache and we build the logic for the cache is, first off, where do we put things in the cache? That's our first question we have to answer. Second question, which is directly related to it, is how do we determine whether or not the value we requested is actually in the cache or not? The third one, which we won't get to today, what happens when we have more things we want to put in the cache than would actually fit in that particular cache? That's going to happen, right? Our main memory is gigabytes, and our cache is kilobytes to megabytes at most. There's more things in our main memory than are ever going to be in our cache. How do we deal with replacing things in the cache? What value that's currently in the cache do we get rid of? That's our cache replacement policy. That's question 3. And then question 4 is how do we handle writes in the cache? Reading from the cache is what a lot of these examples will be showing. What do we do when we want to write a value to the cache? The reason that's a separate question than questions 1 through 3 is because there's an issue with consistency of our main memory. If I write a value, if I don't have some mechanism to take advantage of this, I wind up in a scenario in which a request to the cache returns one value and a request to our main memory returns a different value. That can be okay as long as we're aware of that fact, that depending on whether it's in the cache or not, you have a different value. The value could be quote unquote wrong if we read the stale, if we read the old value that hadn't been written to yet. So today we'll just focus on 1 and 2. We'll do the best we can on questions 1 and 2 today. And then on Wednesday we'll jump into 3. 4 will come either at the end of this week or in the very beginning of our final week of the semester. The simplest design for a cache is referred to as a direct mapped cache. And it's a simple design for a cache, but it's not an invalid design for a cache. You still quite frequently see direct mapped caches in all sorts of things. Nicholas, your question about multi-core is very valid, and I don't want to get into it because that issue with write consistency is especially important for that instance. So a direct map cache is our simplest approach. Each main memory address has a direct mapping to one location in the cache. So for this particular example, which is just beautifully color-coded here, we have a 16-byte main memory. We could have drawn this larger. This could have been an 8 GB main memory, but the PowerPoint slide would have been very large. With our 16-byte main memory, how each of those entries in our main memory, again, this is the address that your load word and store word is calculating, how that maps to our particular location in our cache. And that's what the color coding is trying to show. We just have a 4-entry cache for this particular instance. So we just color them red, blue, green, and I don't know, magenta, pink, whatever that is. And the equivalent color coding corresponds to then which main memory locations would map to that same block in our cache. So for this example, main memory addresses 0, 4, 8, and 12 all map back to that same index in the cache, index 0 in the cache. Likewise, 1, 5, 9, and 13 all map to index 1 of the cache. 2, 6, 10, 14 all map to green and so forth. It's a direct mapping, meaning there's only one place it can go. That's all that direct mapping means. Visually, we see that's the case. And I think visually it also kind of makes sense, right? We have 4 entries in our cache. So roughly each of them has to be responsible for 1/4 of our main memory, right? For kind of a fair distribution of main memory locations to our cache locations. That would be one way to do it. This is the simplest way of doing it, but it's a valid way of doing it. How do we compute that mapping? You can see it visually, but we have to have a piece of logic that tells us where it goes. How would we do that? The answer's on the next slide, but we'll get to, I want to get your intuition for it first. Don't look ahead. I saw you click forward. Okay, yes, you're both correct. It would be the 2 least significant bits for this instance if it's a 4-entry cache. It's the exact same as the mod operator, right? 0, 4, 8, 12, mod 4, all give us 0, right? 1, 5, 9, 13, mod 4, all give us 1. So we could do we could do a modulus operator, and that's exactly what the slide suggests here. But because these things are powers of 2, you don't actually have to do any math to do a mod operator. But technically that is the correct answer, right? Given this address, we have 2 to the k blocks in our cache. We would take the main memory address mod 2 to the k. So for this 4-entry cache, everything would be mod 4. That is the correct answer. Because it's a power of 2, we don't actually have to do any division or modulo operators or anything like that. Because it's a power of 2, those 2 least significant bits of our address are going to correspond to our block index, are going to correspond to our address into the cache. It's an equivalent way. This is the correct, appropriate way. This is all related, right? This is why our caches tend to be sized by powers of 2 for this exact reason. This isn't a coincidence here. And for all memory storage, but caches specifically, if your size is a power of 2, that mapping, while still using a mod operator, can be computed just by grabbing those least significant bits. So again, 0, 4, 8, and 12, mod 4 is equal to 0. That also corresponds to the two least significant bits being 0. Likewise for 1, 5, 9, and 13, the two least significant bits are 0, 1. It's going to always correspond to 0, 1 as our block index. Same for the green, same for the pink magenta value that we have here. So for our direct map cache, you could argue that's minimal hardware. You could actually argue that's zero hardware, right? That's just grabbing those bits from the incoming address signal corresponding to a main memory address, and instead treating that as a cache address, as a block index to grab and check the value in that particular block. So that's our first question. For a direct map cache, we put it there. That's only the first half of that question though, right? That is, what location in the cache corresponds to my main memory address? The second part of that question is arguably the more important one. If we have things in the cache at that location, there's something at location red at 0 here. The example given here is the green one. So we'll say there's something stored in location green here. We know if we have a green address coming in that we're going to want to check the green block in our cache. So if our address is 2, 6, 10, 14, we know at least which block to check. And we can check if something is there. But how do we know which one it's there? You can think of this as an address aliasing. You can think of this as a conflict in our cache. It's always going to be the case. Our cache is always going to be smaller than our main memory by definition. That we're going to have many, in this case it's only 4, but ultimately many significant orders of magnitude more main memory addresses than we have cache addresses. So we have to have a reliable and guaranteed way to determine which of these 4 green possibilities is actually the value that's stored in my green location here. You can think of this as a hash function, right? It is, right, in terms of taking a large input and distilling it down to a smaller output. And taking least significant bits is a mediocre hash function here. It's going to have lots of conflicts. There's no uniqueness properties or anything like that of it. But it's a way of hashing your large addresses into smaller addresses here. You can do that. You can think of it that way. We still need to have some mechanism to tell us, okay, here's the address I've calculated for my index to the cache. What's actually there? Which value do I actually want to have there? And that's a so-called tag field that's corresponding to this. So the idea of tagging our data in the cache, you can think of it as metadata. Metadata tends to have a connotation of something that provides additional meaning to the raw data that we have stored somewhere. And absolutely that's what these tags are doing here. These are additional bits of storage in our cache that are there specifically to disambiguate which main memory address actually corresponds to our cache location. We're tagging the values. One way to then do that lookup is to first calculate our cache address, read the value from the cache, and determine if the metadata that's stored in the cache matches what you expect for that particular location. For this type of cache, for this direct map cache, what would be the metadata, the tag that we would actually then store in the cache would just be the remainder of the address bits. So in this case, because it's a 4-entry cache, the 2 least significant bits are being used as our block index into the cache. To disambiguate between address 6 and address 10 here, the only thing that's different about them would be the remainder of those address bits. So not only do we store the actual data, that's what this is still trying to indicate here, the actual data, the 32, or in this case 1 byte value we're interested in, we also need to store in the cache that metadata. We also need to store those tag bits in the cache as well. This is overhead, right? We have a cache of a certain size of data we want to store, and to get our cache to work properly, we also have to store this other information. In this case, those tag bits are what we have to store here. A question I often receive, and I haven't gotten it yet, we'll give it time, but is why don't we just store the whole address in the cache as well? That would be one way to fully disambiguate whether or not we have the right value here. And we could. There's nothing wrong about storing the entire value in the cache for that purpose. But we just don't need to. Taking the 2 bits used for the index combined with the remainder of the bits used for the tag uniquely identifies each location in the cache. Lower bits tell us which row in the cache we're looking at or which index in the cache we're looking at. the upper bits, the remainder of the bits, tell us which main memory address it corresponded to. So you could store the whole address, you just don't need to. Taken together, we have the entire address here. We're just not storing the lower order bits, we're directly using them. So it fully disambiguates what's in our cache just by adding the remainder of the bits for that tag. So taken together, we can directly determine what main memory addresses are served in the cache via combination of what is our actual index into the cache as well as with our tag bits here. You can always reverse that operation to determine this is entry 2 in the cache, that's index 10. If the tag here is stored as 01, that is what the main memory address is corresponding to in the cache. So in order to determine whether the value we're interested in is in the cache, there's those two things we have to do. And as we'll talk about in a second, there's a third thing. We have to calculate which row we're interested in. To be a little careful, I keep calling it a row. It's not necessarily a row because it's not necessarily laid out in such a fashion. We have to calculate what location in the cache we're interested in, the index in the cache we're interested in. And we have to fetch not only the data we're potentially interested in, we also have to fetch those tag bits. So even though we're only requesting an 8-bit value here, we're actually going to fetch a 10-bit value. And it's going to be stored in the cache as a 10-bit value here. 8 of those bits are going to be the value that our load is going to return. It's the value we're actually interested in. The remainder 2 bits are just there to check. Hey, is this actually what I wanted? Is it the correct address that I was looking for? Or is I was wanting 6, or I was wanting location 10, but it's actually location 6 stored here. Even though there's something in the cache, it's not the right thing. That's a cache miss. And finally, the last thing we have to add for that cache storage, another bit of metadata or overhead, is we need to have some way of keeping track of, hey, is there anything valid in here or not? Right? We think of our model sims having these floating X's when nothing's been defined properly, but our actual hardware, that's going to correspond to a 0 or a 1 in terms of system reset, in terms of when our program starts up. So we are separately going to store a valid bit, an additional 1-bit value that keeps track of, is there anything good in this cache location yet or not? So when our system is initialized, that column, that valid bit per entry in our cache, would be initialized to all zeros, meaning nothing's valid in the cache. That also gives us a very simple way of flushing the cache as well. You don't have to overwrite all this stuff in the cache. We just have to set this whole column to zeros. And in doing so, you're telling the next program that's accessing it, there's nothing valid in this cache for us. So we set those values all to 0. When it comes time to actually initially load a value into the cache, then we would overwrite that with a 1. Initially, there's nothing valid in there. As soon as we finally put something in that location, then that value gets overwritten to a 1. We have the actual data we want, we have those tag bits that we want, and then we have those that valid bit. It becomes valid, and that's not quite precise. It becomes valid as soon as we put something in there. So again, that initial access, if that column is all initialized to 0, it's always going to be a miss. But in the process, we grab the value we want from main memory, and as we're returning it back to the processor that needs it for the register file or the next instruction, we also update the cache. We update the tag, we update the data, and we make sure we set that valid bit to 1 so that we know the next time around, yeah, there is actually something valid in that cache at that point. Architecturally, then, we can take this information and start to lay it out here. Before I do that, let's do a brief in-class exercise. I could partner you up, but I'm worried that half of you are only just kind of logged in case there was a quiz, and then you'll be partnered up with nobody. So I'll just have you do this kind of by your lonesome here briefly over the next minute or so. So consider the 2 following cache structures. This is a homework type of question. In fact, a very similar question is actually on the homework. That's a 4-entry cache on your left there, and that's an 8-entry cache on the right. So for the following memory accesses, what are the hit-miss results for the 2 different caches? I'd like you to take a minute and work your way through that problem. The second question, we don't have to work our way through. We can discuss that together. So take about a minute, and you probably would want, you don't have to write down a lot of information, but you probably do want a piece of paper or something that you can scribble on because this is not something you'd want to be able to keep track of in your head. Are these hits or are these misses in the cache? Let's take 90 seconds and try to work your way through this problem. Then we'll come back together here. There's some very heavy equipment going on right outside my window right now. We've made it pretty far this semester without this happening, so it's okay. We did pretty well this semester, so no worries about today being a little tricky for me. Okay, so if you didn't get all the way through it, that's fine. 90 seconds is probably not enough time for your first time tracing through cache. Let's try to do it together here. Um, and the truth of it is, you really can't do this type of question without writing it down, because you do have to kind of map what's happening to these accesses as they go here. Let's see if we can actually do some writing. Okay, great. Well, we're just going to keep that scribble there. So you just trace through. You trace through exactly what's happening with each access, and just figure out where things need to go. And it's again just based on the addresses. So there is a little bit of a fluency assumed here, and that's that kind of like decimal, that base 10 to base 2 conversion. Um, I would argue that if you're having to use a calculator to figure out what 5 is in binary, you're at a disadvantage, right? I'm not saying you can't do this problem. I'm not saying you're not going to be a wonderful engineer after you graduate, but there's kind of a fluency that's sort of expected at this point. I told you you'd be fluent in hex by the end of this semester, and based on what I saw for Project Part B, that has been the case. But by and large, when dealing with architecture, certainly also when dealing with embedded systems, we have to have that kind of fluency. So for these accesses, it should be relatively quick for us to determine where things are going to be stored in our memory based on just that encoding of the addresses. So when I say mem of 0, I guess I could say memory at location, main memory location 0 is what I'm getting at here. So it's the 0 that matters here. It's location 0. So in both caches, both the 4 entry and the 8 entry cache, we're fine, right? 0 gets stored here. And consequently would also get stored here. Because if we were to look at that encoding of 0, it's 0, 0, 0, 0, right? The tag bits would be different. It's a little tricky here because we're not actually updating these tag bits. The tag bit would be just a 2-bit value for the 4-entry cache because there's 2 more bits of address. But we only actually would need a 1-bit tag for the 8-entry cache because there's only one other address here. And then finally, we would mark them both finally as valid. But the question is actually asking, don't show me what the cache looks like. What are the hit-miss results for the 2 different caches? So is that a hit or a miss? It's a miss, right? Our cache is empty to begin with, or our cache is completely invalid to begin with. Human memories, we take 1 extra minute here. So it's empty to begin with. Next access comes, we can go through this relatively quickly. 0101, that corresponds to this location in this cache. But now at least we can see a little bit of difference. That's going to correspond to location 5 in this cache. We could be updating the tag bits as we go, but in this case, this tag bit would then be 01. That's also going to be a miss. Next comes address 10, 1010. In this cache, that corresponds to this location. In this cache, it would correspond to location 2 now, because now we're taking mod 8 for this one. But that would also be a miss. For our temporal locality, we're only ever going to get a hit when there's a repeat. That's our only chance at hit when something repeats. So as we're doing these initial accesses and there's no repeats, there's going to be no hits until there is at least an attempt at one. Finally, mem of 7. It's possible I made a mistake, but I didn't. Okay, memory of 7. Our tag for this one would be 11, so it'd get put here. Or our index of this one would be here. Whereas our tag or our index is the 3 bits for our 8-entry cache, so memory of 7 would go up here. And of course, that's also going to be a miss. Yep. And we will talk about why the tag bits need to be our higher order bits. If we don't talk about it, it'll make a good homework question. We have 0, 1, 0, 0 for 4. Let's talk about at least what happens in that case here, right? For the smaller cache, 0, 0 corresponds to index 0, that is still a miss because the value that was there was memory of 0, and now we're going to override it with memory of 4. Whereas in this cache, 100 is its own separate location in the cache. It's still going to be a miss because it's our first time accessing it. Our first possibility for a hit comes when we access memory of 0 again. Again, that's the same as it was before, 0, 0, 0, 0, so that's a miss. Um, when we access 0 again for the smaller cache, we just missed it, right? We're just out of luck here. Right? We had it and then we lost it because our locality wasn't good enough for this small cache to take advantage of it. That is a miss in our smaller cache, and then this value gets overwritten again. Whereas in this cache, because we had a few more entries, that's our first hit. Finally, after all that. And I think you can see where this is going from here. As we access 4 again, that will be a hit on the larger cache, but a miss again. We'd have basically a thrashing effect on our smaller cache. Um, we'll go through a little bit more of this exercise on Wednesday. For now, just having a basic fluency of what it means to have locations in the cache, how we calculate those using that mod operator or just taking the least significant bits, and what we do with the remainder of those bits and why we need to have the remainder of those bits is sufficient for today. So let's leave things here for today. And Wednesday, we will have a quiz just covering this basic topic of locality and cache basic storage. And then we'll talk more about the digital logic. What does it mean to actually implement this in practice? Based on some of the questions, one-on-one questions I got here, I think a lot of you are already starting to get that. But we'll just cover it, and then we'll look at what does it mean to now have more advanced cache structures. They get a little tricky as we get into some of the more nuanced aspects of it. But I think certainly by Wednesday, we'll have a pretty good handle on our direct map caches and what that means from an architectural perspective. So let's leave things here for today. And everyone, looking forward to seeing you on Wednesday.